on lines. Okay, so we're going to get into two types of graphs in these next upcoming sections, 2.3 and 2.4, and they couldn't be more opposite of each other. A line, perfectly straight graph, no curvature whatsoever, and then a 2.4 is a circle, in which case there's constant curvature around it. And then to wrap this chapter up, section 2.5 is an application of linear equations involving something called proportions or variation. So let's start with lines. Here's how our author defines it. A line is the graph of a linear equation. And I hope you guys were sitting down for that, because that is like the world's most earth-shattering news, right? But that's one way of defining a line. Another way, which I was presented this in my graduate studies, it gives you a little bit more of a visual. It's a series of points that extend indefinitely in opposite directions. All right, so you got a bunch of points that you're plotting, and they just kind of extend in opposite directions. And the more and more points you include, the more and more it takes the form of a solid line. So I'm sure we all can visualize what a line is. I'm not going to, get us bogged down with that. One important feature of a line, though, is something called the line slope, which I'm sure you may have heard of before in the past, especially if you've worked with lines. And a slope is something that we can calculate when the line is in the coordinate plane. And how you calculate it is by forming a ratio or a fraction. And this fraction will have a numerator and denominator, obviously. And in the numerator, we have what's called a vertical change. And in the denominator, we have what's referred to as a horizontal change. And these changes are calculated by taking 2 points that are on the line, and it can be any 2 points. And so this ratio of the vertical change to horizontal change between any 2 points will always give you the same number. And that's why it says here is always a constant value. And this constant value, or this number that you get when you form these ratios, is known as line slope. And we typically indicate that with the letter M. So I have a diagram with 2 points on a line, generic coordinates, and that's because I want to give you one version of slope that involves a formula. And in the box to the right, you can see that I'll be giving you a total of 3 versions of slope. The first version of slope involves these expressions, vertical change and horizontal change. Let's imagine that we're at the point with coordinates x1, y1, and we want to travel to the point x2, y2, but we're only allowed to move left, right, up, and down. So there's no traveling diagonally. One way to get from the point x1, y1 to the point x2, y2 is to go as far to the right as possible until you're underneath the point x2, y2. And this is what we mean by horizontal change. And horizontal change can be more succinctly described as a run. All right, so horizontal change and run are interchangeable. Now that we're underneath the point x2, y2, we can go up to that point to finally reach our destination. And how far we go up is what we mean by the vertical change. And there's an R word for this as well. It's rise, exactly. Yep. So vertical change is interchangeable with the word rise. Rise over run, exactly. So keep in mind that the slope is a ratio of the vertical change to the horizontal change. And so my first version of slope for you folks is rise over run. And this is a good form of slope to have when we're trying to calculate an actual number for it based on a graph that's already provided to us. The next version is helpful when we have 2 points on the line like we do here, and we want to calculate the slope using their coordinates. So I'm going to label the x-axis and y-axis based on how these points are written out. So I'm back down at this bottom point. Directly underneath it on the x-axis will be its x-coordinate of x1, and directly to the left of it on the y-axis will be the y-coordinate y1. And I'll do the same with the very top point. With the tick marks on both x-axis and y-axis, there are these gaps between them. If we look at the x-axis, there's this gap between x1 and x2. The length of this gap happens to be the same length as the run that we've indicated. And so we can figure out how much the run is by figuring out how much is separating x1 and x2. And to figure out how far apart x1 and x2 are from each other, we can just subtract them, x2 minus x1. That would give us the length of the gap, which in turn gives us the length of the run. The gap that's separating y2 and y1 is found the same way. You can subtract y2 minus y1 to figure out how long that gap is separating y1 and y2, but it would also match up with how long the rise is. And since slope is rise over run, we can replace the word rise with an expression, and that would be y2 minus y1. And then the run can get replaced by x2 minus x1. All right, and this is a helpful version of slope to have when your instructions don't necessarily give you the graph of the line, but maybe a couple points that are on it. And have you guys seen this version of slope before? Rock on. Now I do want to let you know that this is equivalent to y1 minus y2. So you can switch the y values on top, but you have to make sure you switch the x values on the bottom as well. So if you're going to do y1 minus y2, be sure to do x1 minus x2 on the bottom. So in other words, the subscripts have to go in the same order. So in the first version, it goes 2 and then 1, 2 and then 1. In the second version, it goes 1 and then 2, and then 1 and then 2. The last version of slope is helpful for application problems. Have any of you folks seen this type of notation before? The triangle in front of a variable? Maybe if you've taken like chemistry or physics or anything like that. Exactly, yep. This triangle is the Greek letter D, the capital version of it actually, and its proper name is delta. And in the context of math application problems, or Math-E type of application problems, it can sometimes refer to the expression change in ... So with this very last version of M, we can read this off as change in y over change in x. And it's helpful for application problems because we can model what's called a rate of change in this format. Okay, so things that are changing over time. All right, do you have any questions for me on any of that? Okay, well, I think now would probably be a good time to take a 5-minute break. When you come back, we're going to put the slope to use and look at a couple of equations that can be used to model lines, and then move on to some applications. All right, so let's go ahead and take a 5-minute break. I will see you once that's over with. All right, gang, you ready to rock and roll? Here we go. All right, one of the first skills that I'd like to go over is graphing a line, given that we're provided a point and the line's slope. So this is a helpful skill to have when working with lines that are in slope-intercept form, which is one of the first forms we'll talk about on the next page. And it's really just a two-stepper. If your problem provides you a point, the first thing you're going to do is plot the point. And then based on where that point is at, you're going to use your slope to plot a second point. And this is based on where you plotted the point in step one. And the way to use the slope is to think of it as rise over run. Okay? And you can continue using your slope to generate more and more points. And I'll let you know the more and more points you have, the more accurate your graph will be. But if you want to be a minimalist like me, you only need 2 points in order to graph the line. All right. So step 3 is kind of an optional one. You'll use the slope to plot more points if desired. And each new point that you plot is going to be based on your most recent one. Symbolically, step 1 is to plot the point that's provided to you. I'll just write it generically as x1, y1 for now. And then step 2 is to use your slope. And the version of it that you'd want to use is rise over run. Now, just a quick note about that. Rise, that number could be positive or negative. So I'd like to examine each case. If the rise is a positive number, what that means is that we'd have to go up by whatever number is in the numerator. Whereas if the rise is negative, that would tell us to go down from the point that we plotted in step 1. So when you're using your slope, the first movement that you do is either up or down, and that depends on the sign of the rise. The run could be positive or negative. And if the run is positive, anybody know what direction that tells us to go into? Go to the right. Yep, that's right. Whereas if the run is negative, that would tell us to move left. Now we always do the rise first, and then based on where we land after we do our rise, we do our run. And then after we've done the run movement, that's where we settle down, or we settle down and put our point at. So with that, our example is to sketch the graph of a line that has a slope of -2/3 and passes through the point -1, 3. So -1, 3, those are specific values of x1 and y1. Let's go ahead and plot that point. -1, 3, it's in quadrant 2. Now for our slope, which is -2/3, I want to let you know that there are 2 interpretations that you could do with -2/3. And that's due to this negative sign. This negative sign can be assigned to either the numerator or denominator, but not both, otherwise the fraction turns positive. I want to examine the case where the negative gets assigned to the numerator. This would force us to have a rise that's negative. And since this rise is negative, we'd have to go down by 2 units. the 3 is not negative, it's positive. So after we go down by 2 units, we'd have to go right by 3. All right, so let's see how we do that. Let's start at -1, 3, the point that we just plotted. Using this version of slope, we'd have to go down 2 units and then to the right by 3. And that's where we can get our second point. Now that would be enough to sketch the line out. But I'm going to get a third point going on this graph, and that has to do with the second interpretation of the slope. We could have the 2 be positive this time and the 3 be negative. So with this version of slope, what would the numerator tell us to do? Yep, up 2. And then the denominator, since that 3 is negative, we'd have to go left 3. So let's go back to the point -1, 3. If we use this version of slope, then from -1, 3, we'd have to go up by 2 units, and then to the left by 3. And there's actually no harm in doing that. You do get, in this case, a third point, but if you were to use this version instead of the first version, you get a second point. But regardless, as soon as you have 2 points or 2 or more points, you're in a position to connect the points with the rest of your line, which I'll go ahead and do that. Okay. Any questions about this example? Does that make sense? Or anything I can clarify? You guys good to go? Alrighty. So with that, we're going to focus on certain equations that lines will have. And these are helpful for when we're asked to provide the equation for a line based on specific information from it. It could either be a point and a slope, or it could just be a couple of points. And how we start is with one of these 2 versions of the equation for a line. These aren't the only versions, though. There are other versions, standard form, general form. But these ones I think are the most pertinent to what we have to do. So the first version, probably the most common or most popular one, is the slope-intercept form version of a line. And this is definitely a flashcard-worthy formula. It goes y equals mx plus b. So if we know the slope of a line and its y-intercept, which is what b represents, we could write an equation for that line. So again, I want to emphasize the m that's in front of x is the slope. No surprises there. But the b that trails it, that's going to be the line's y-intercept. And as we just saw earlier with our recap, the y-intercept will have an x-coordinate of 0, and in this case, the y value tick mark will be b. So slope-intercept form is super helpful to have if you're asked to graph the line, because your y-intercept serves as a point, and then your m is obviously your slope. So we could apply the technique that we just did at the very bottom of the last page in order to graph a line that's in slope-intercept form. Unfortunately, you need some very specific information to jump straight to this equation. You need both the slope and an indication of where the line's crossing the y-axis, or in other words, the y-intercept. And in a lot of problems, this information isn't served up to us right off the bat, which is why I've included the point slope form of a line. Okay, so if you don't have this very specific information, both the slope and y-intercept, then you defer to the point slope form, which goes y minus y1 equals m parentheses x minus x1. So a lot of problems will provide you with some info, not necessarily the slope and y-intercept, but a way of finding the slope of a line as well as a point that might not be the y-intercept. So in other words, we typically have to start with point slope form, and how we start is by figuring out what y1 is, what the slope is, and what x1 is. Now I'll tell you where we get these from. Okay, so this is what we need in order to start a line in point slope form. One case, it might provide you what the slope is and a point that's different from the y-intercept, x1 comma y1. And this would be enough to start filling out our equation. In some other cases though, you're provided only 2 points on the line. So x1 comma y1 and x2 comma y2. Now you would have values of x1 and y1 that you could plug into the equation, but you don't have the slope right off the bat, although you could use these 2 points to calculate the slope by using the formula y2 minus y1 all over x2 minus x1. So I would say number 2 here is kind of like the worst case scenario, where it involves the most work for finding the equation of a line. And so I have an example of this worst case scenario. That way, you can dig yourself out of the hole a little easier, so to speak. So let's move on to that. Let's find an equation for the line containing the points -1, 1 and 2, 2. All right, so this is a situation where we do not have the slope, and none of these points represent the y-intercept. So unfortunately, we can't jump straight to slope-intercept form. And if you look at the problem, that's what it wants us to express our answer in. So it'd be nice if they gave us the answer right away, but it's not the case here. So we will have to defer to point slope form. And hopefully that makes sense because we are only provided 2 points on the line, so it's kind of like a case 2 situation. So I'll take you through a 3-step process, which will help us achieve the equation of a line in slope-intercept form. I like to call it a conveyor belt process. Number 1, first thing we're going to need to do is find the slope m. Now, these 2 points, I just go in order from left to right. I'm going to have this -1 represent x1 and the +1 represent y1, which means that this will be x2 and y2. Can I ask that you calculate the slope? All right, once you have the slope, feel free to type it into the chat bar and we'll go over it. That's half of it. There it is. Yep, so let's see why it's 1/3. And once we go through that, Isabel, let me know if it makes sense. So the numerator is y2 minus y1. That's going to be 2 minus 1 on top. And then the denominator is going to be x2 minus x1. So we'll take 2 and we'll subtract -1. On top, 2 minus 1 is 1. And on bottom, there's a double negative, giving us 3. Well, that's why we'd have 1/3. Does that make sense? No problem. I appreciate you volunteering the answer either way. All right, so that's the first step. The second step in this conveyor belt process is to plug any information you can into the point slope version of the line. Remember, it's y minus y1, and our value of y1 is +1. So y minus 1 equals m, which we just got done calculating, is 1/3, times quantity x minus x1. So we're looking at x minus -1. I'm just going to clean that up a little bit. I'll keep it as y minus 1 on the left, 1/3, and in the parentheses, due to a double negative, it'll be x plus 1. And this technically is an equation for the line, but it's not in slope-intercept form like they're requesting. All right, this would be the point-slope version of the line. Which takes us to the third and final part of the conveyor belt process. This is where we're going to rewrite that equation in the format y equals mx plus b. So let me jot down what we just got in step 2. Now notice in slope-intercept form, there are no parentheses, but we have parentheses. What's something that we can do to fix that? Distribute, yep. We're going to distribute the 1/3. So we get 1/3 x plus 1/3. On the left, we still have y minus 1. Another thing to notice about slope-intercept form is that y is by itself. Our variable y is not by itself, but how could we quickly fix that? We could add 1 to each side, yep. So y equals 1/3 x, and off to the side, let's grind out this fraction work. We have to do 1/3 plus 1, which, based on common denominators, let's write the 1 as 3/3. And adding 1/3 to 3/3 will give us 4/3. So in other words, when we combine positive 1/3 with positive 1, we get the fraction 4/3. So this is officially in slope-intercept form. Our slope is 1/3. Okay, we knew that. But what we didn't know until now is what our y-intercept is. Now that this is in slope-intercept form, we know that the y-intercept is at 4/3. And that's where the pain and torture, fun and excitement for this example ends. Is there any part of this that you need me to go over? All right, so the next couple of equations are kind of like special cases. These handle the situations where we have a horizontal line or vertical line to work with. And these are, again, flashcard-worthy formulas and facts. I'm going to include some information on this diagram, both of them actually, to help us understand where the equations and slopes come from. Okay, I'm a firm believer that understanding where stuff comes from helps with the memorization component. Let's assume that this horizontal line crosses the y-axis at 0, 5. Now, all the other points on this line are directly to the left and directly to the right of this point 0, 5. So let's say that I wanted to look at a point on this line that had the x-coordinate of 1. Could anybody tell me what the y-coordinate of that point would be? The y-coordinate of this point? It'd be 5. Yeah. So the fact that the y-intercept is at 0, 5 means that it crosses the y-axis at the tick mark of 5. So any point directly to the left or right of the point 0, 5 is going to have a y-coordinate of 5. And that's because every point on the line will be at the same height as the y-intercept 0, 5. So for example, if I went to the other side and wanted to look at a point that had -2 as the x-coordinate, it's safe to assume that the y-coordinate would be 5 because -2 is at the same height as the y-intercept is 0, 5. Does that make sense? All right. Now, looking at all three of these ordered pairs, what's one thing that is staying the same? The y values. So one way of describing the equation for this line is to state the fact that y is always equal to 5. In fact, that is the equation for this line, y equals 5. In general, the equation for a horizontal line is always going to be y equals some number b, and it's not just any random number. This b is the value of the y-intercept. Now the slope, one way of figuring out the slope is to use the formula y2 minus y1 all over x2 minus x1. And you can pick any 2 points from this line to do this with. If we picked 0, 5 and 1, 5, and let 0 be x1 and 5 be y1, and 1, 5 be x2, y2, then the numerator would be 5 minus 5 all over 1 minus 0, giving us 0 over 1, and 0 over 1 is 0. Meaning that the slope of any horizontal line is always going to be 0. Okay, Now for a vertical line, which is the type of line in our next diagram, let's assume that it crosses the x-axis. I'll use a different number this time. Let's say that it crosses the x-axis at a tick mark of 3. Then the ordered pair for that point would be 3, 0. And if I wanted to take another point on this line, let's say a point that's a little bit higher than this, let's assume that the y-coordinate of that point is 1. Could anybody tell me what the x-coordinate of that point would be? 3. Yep. If I had a point maybe in quadrant 4, and I'm just going to throw a random y-coordinate on there. Let's say that the y-coordinate is -3. Can anybody tell me what the x-coordinate is? 3 as well. Yep. So since all these points line up with each other, in order to plot a point on this line, I'd have to always go 3 spaces to the right and then up or down however much based on the y-coordinate. So all these points are the same units away from the y-axis. They're 3 units to the right of it. Looking at all 3 of these points, this time the x-coordinate is always the same. And one way of describing that fact is to say that x is always equal to 3. And that actually happens to be how we would write the equation for a line such as this. In general, the equation for a vertical line will always be the format x equals a, and not just any random value of a. That value of a will be the value of the x-intercept. Anybody have an idea of what the slope of a vertical line might be? Nope, try again. Yeah, I'm going to go with undefined. I'll say UND for short. No problem. So we could actually use the formula for slope to see that. Let's maybe have 3, 1 be x1, y1, and 3, 0 be x2, y2. You can pick any 2 points. It doesn't have to be these 2. But we'll roll with these 2. And if we use the formula for slope, the numerator would be 0 minus 1. Denominator would be 3 minus 3. And we'd end up getting -1 over 0. And keep in mind that when 0 is underneath a fraction bar, that's when we get a value that's undefined. So do you guys remember my less than and Great Tour cheesy Mr. C tricks, memorization stuff? Well, I can't take credit for these, but I have a couple of acronyms that you can use to help you with the skill of writing the equation for horizontal or vertical line. Let's start with the horizontal. The acronym that you can use for horizontal, this is, by the way, a pirate's favorite acronym, is HOI, as in ahoy matey. The reason why it's an acronym is because H is going to stand for the word horizontal, more like horizontal, Mr. C. The O is going to double up as a 0, meaning that 0 is what the slope is equal to. And then the Y gives us the format of the equation, which we just saw a minute ago, that it's y equals b, where b is the y-intercept. I am curious, has anybody seen this before? The acronym HOI? All right, well, you're welcome to use this to help you out with any problems involving horizontal lines. The other acronym is for vertical lines, as you might expect. And this is VUX. Emphasis on the v. All right, so VUX, as you might expect. The V part of this stands for vertical. The U stands for undefined. I'm going to say UND is equal to the slope. And X stands for the format of the equation, which is X equals A, where A is the x-intercept. Okay. So we have 4 equations for lines on this page: slope-intercept, point-slope. Yeah, there we go. Substitute. Yep. I gotta be honest. Anytime I am presenting the VUX, that just comes across my mind. So anyhow, yep, we have 4 equations for lines. We got point slope, slope-intercept form, and then we have the special cases of horizontal and vertical lines. And this is really about all we'll need moving forward with the rest of the material in the course. All right, so any work with lines, you know, can be directly linked to, you know, the information on this page. Like I said, there are other versions of equations for lines. Those don't really take as much precedence as these ones. For instance, in the case of application problems, so there are lots of applications of lines. I plucked out a couple of examples that are more real life in nature. We're going to work through this one together, and based on where we're at time-wise, we'll do another warm-up session on Wednesday with the very last example. So one application of lines involves calculating costs for things you know, such as utilities. It could also be cell phone bills, lots of applications of lines. A lot of cases modeling, you know, financial things. In this case, we're going to be looking at an example where we'll model the cost of using a company's electric supply. And it's going to be a monthly cost. And in this you know, description here, it says Commonwealth Edison Company supplies electricity to residential customers for a monthly customer charge of $15.14 plus, I know this is weird, but apparently this is how rates are given, 7.57 cents per kilowatt hour for up to 800 kilowatt hours. It says write a linear equation that relates the monthly charge C in dollars to the number X of kilowatt hours used in a month. Now, at the tail end of this, we have this compound inequality where it says X is between 0 and 800. We actually don't need this information to write the linear equation, but I will come back to this part of the problem and show you how you can use this to generate the graph of our line using the graphing calculator. So part A what we want to do, and I'll write this as like a goal, we want a linear equation, and the format of the linear equation that you want to assume here is slope-intercept form. And that would definitely be the ideal form to have anyway if we want to do anything on our graphing calculator, because this is one where y is isolated. But they don't want us to use y. Instead, they want us to use c. And so I'm going to rewrite this as c equals mx plus b. Now, as you might tell, in order to do this, we're going to need the slope and y-intercept. Although you don't have to do it for this problem, I'm going to do it anyway because we're going to need to use this technique for the very last example of the notes. I'm going to make a table of values. And in the first column, we'll have values of x, which, keep in mind, these values of x represent the number of kilowatt hours. And then the column to the right will be the associated cost. Now, before we get going with values in this table, there's one subtle but important detail within the first part of the example where it provides us the information about costs. It's this guy right here, 7.57 cents. We have one number provided to us in units of dollars and another number provided to us in units of cents. If we look at part A, what it says in it, they want our cost to be in terms of dollars. So what that means is we should consider converting 7.57 cents to dollars. Could anybody type in the chat bar what the equivalent version of this is in dollars? Perfect, yep, 0.0757. So we need the units to match, and the unit to use is dollars because that's what they're requesting of us in part A. So with that little detail taken care of, let's go ahead and see how we can fill out this table. And I'll pose this as a question. Do you think there's any cost to the customer that gets their electricity from this company if they don't use any kilowatt hours in some given month? Do you think this customer still has to pay something if they don't use any kilowatt hours? Yep, they certainly do. How much would they have to pay even though they don't use any electricity? $15.14, you got it. Yeah, so there's this customer charge of $15.14. Well, that's known as a fixed cost. And it's kind of like a fee to utilize a company's services. Maybe it helps them keep the lights on. No pun intended there. But anyhow, yeah, if you're enrolled with this company, getting electricity from them, and if you don't use any electricity in a given month, you still have to pay this customer charge. All right, so it's a fixed cost, and those are quite prevalent in the real world. So here we go, $15.14, 15.14. If we think in terms of the graph of a line, this would be translated into an ordered pair at 0, 15.14. What I'd like to do is get another ordered pair on this line by filling out, this table with one more x value. And by getting a second point, it opens up the opportunity to calculate the line slope. So what I like to do is I like to just increase x by 1 and consider what the cost would be if only 1 kilowatt was used in a month. So to figure that out, keep in mind that there's always this customer charge of $15.14. Now, if I used 1 kilowatt hour, I would have to add 0.0757 to that. Well, yeah, I would agree with that if we wanted to round that to the nearest penny, but I'm going to keep it in the exact form. And the reason for that is because I want to make a connection to one of the numbers in the problem with the slope. If you add these two together and don't round, you get 15.2157. And this would give us a second point on the line with an x coordinate of 1, and then that is its y coordinate. And with these 2 points on the line, we can calculate the line slope. Okay? Now to find this line slope, I would use the formula y2 minus y1 all over x2 minus x1. The first point I'll allow to be x1, y1. The second point I'll allow to be x2, y2. And if you plug these into the formula, we'll get our slope. And I'll give you a second to punch that into the calculator if you want. Once you think you have the value of the slope, go ahead and type it in. Precisely. I'm getting 0.0757. Daniela, do you maybe want to? Oh, okay, got it. That's what I thought, that because the last 2 digits were the same. So, all right, cool. So this is our slope, which happens to be the cost per kilowatt hour. So the slope is actually buried in our problem, and it was staring at it. It was hiding in plain sight, essentially. So you might be wondering, why did we bother with the table? Well, the slope won't always be provided to us right off the bat, as you'll see in the next problem when we take care of that on Wednesday. So I always show a table approach just in case the slope isn't given right off the bat. Now, we actually have the value at the y-intercept somewhere in our work. Can anybody spot where that might be? I'll keep in mind the y-intercept is the point with an x-coordinate of 0. Do we have a point on this line with an x-coordinate of 0? We do, and that would be this one right here. All right, see its x-coordinate is 0, so this 15.14 is actually a value of b. So putting all this together, our equation would be c equals our value of m, 0.0757, x, plus our value of b, which is 15.14. And at long last, we have the equation for our line, which happens to also model the monthly charge, to use this electricity. Now, this equation is probably only good for up to 800 kilowatt hours based on the compound inequality in Part A's description. Anything beyond that probably gets modeled a little differently, but we don't have to worry about it. We just have to worry about the equation for when we use between 0 and 800 kilowatt hours. What's nice about having the equation, though, is that we can pick any random value between 0 and 800 and quickly calculate its cost. And that's what example part B is all about. Okay, what is the monthly charge for using 200 kilowatt hours? What do you think we'll do to solve this? Multiply by 200. Yep, there's going to be a multiplication by 200, but don't forget there's always that monthly customer charge. So 200 kilowatt hours is actually a specific value of x, and it'll really just get plugged into our cost formula, right? So we could do it that way. We could do c equals 0.0757 times 200, and then the rest of it plus 15.14, and that there represents the monthly customer charge. And this works out to be $30.28 if you round to the nearest penny. All right, so we're just about out of time. Let's take care of part C, and then go over any questions that you have. And then once those are done, we'll be done for the day. Interpret the slope of the line. There's a particular way of doing this. And what it means by interpret is to provide just a little blurb, verbal description about what the slope really represents in this context. Now our slope, 0.0757, and I'm going to write that on top of the number 1 because I can make a connection to the rate of change version of slope, which change in y over change in x. But remember, the y's are replaced by c. So the numerator here is a particular value of delta c, change in cost, and the denominator change in x, or change in kilowatt hours. And as a tip, all right, we're going to interpret from bottom to top. And what I mean by that is we're going to start by seeing what the 1 represents and then making a connection with that to what the numerator represents. Keep in mind that the X values represent kilowatt hours. If we think rise over run, the 1 is positive. Okay, so if we were to use slope to plot a point on the line, we'd have to go to the right by 1 and then up by 0.0757. So what this is saying is that as you increase the number of kilowatt hours, the cost increases. Specifically, each increase of 1 kilowatt hour increases the monthly cost by $0.0757. All right, I'm going to do my best to have us squeeze a graph into some of this blank space in part A. The problem doesn't require that we graph the equation, but there may be a few problems in my math lab where the graph of the equation is involved. So just to kind of recap, we were working with linear equations, lines, and all that jazz, section 2.3. We looked at some of the essentials of that section. There are plenty more details within it, but the essentials of it for us would include how to graph a line given a point and a slope, how to write the equation for a line, and how to model certain problems with linear equations. And that's what this example and the very last one is all about. So for this example, our goal was to write a linear equation which generates costs for certain usage of electricity. And so we went through sort of a table method in part A to construct our equation, and in part B we utilized it to predict a monthly charge, and then in part C we kind of broke down what the slope meant, in plain old English. I'd like to include the graph as mentioned, and we're going to be graphing the cost equation, which is what I have clouded down here, and we'll do so in the graphing calculator. But let me just jot down what we want to put into y1. y1 is going to equal the expression for cost, so 0.0757 x plus 15.14. And in this type of application setting, we'll probably want to shave off some of the parts of this line that we'll get that don't really apply to the setting. For instance, hopefully we don't get like a negative cost, and we don't use like negative electric amounts. And what I'm alluding to here is that there's a certain section of the graph that is really the only part that applies to this sort of setting. And what all that means is we'll be making some window setting adjustments. So we'll look at a sensible value for x min, 1 for x max. We'll see if rescaling the x-axis might be helpful, and then the settings for the y-axis. Okay, so let's go to our graphing calculators. I got to get mine going actually. There we go. All right, we'll go to the y equals menu, and let's type in the expression for cost, 0.0757, don't forget the x, plus 15.14. All right, if you did zoom 6, not going to see the graph. And there's definitely reasons why, just based on the equation. But like I said, we are going to want to maybe adjust the window settings to settings that are more sensible to our application setting. So keep in mind the X values represent the different usages or the different amounts of electricity being used within a given month. That compound inequality, that's part of Part A's instructions, that's where it says X is between 0 and 800. The 0 is a value of X min that we can use. And then the 800 part of it is a value of X max that we can use. And as I mentioned on Monday, the condition on X that it has to be between 0 and 800 is basically the company's way of telling us that they're modeling costs this particular way when you're using no kilowatt hours all the way up to 800. Anything beyond 800 probably has a different equation that they model costs for, but we don't have to worry about that. I'm going to change the X scaling to 100, just so that there's not a whole ton of tick marks on the X-axis, making it super thick. The Y values represent costs here, and we know that the minimum cost is $15.14, but I'm going to go just a little bit lower than that and set the Y min to 0. Now for the Y max, I'm going to go back to the notes. So 800 is the largest possible X value that is relevant to our equation. And I'm emphasizing that because it helps us with a Y max value. We can get an idea of what to set Y max to once we know what the cost is associated with using 800 kilowatt hours. Okay, so to help out with this Y max value, we can plug 800 in for X, so 0.0757 times 800 plus 15.14. And when you do so, this comes out to $75.70. So the largest possible cost to the residential customer, that is if they use up to 800, if they use 800 kilowatt hours in any given month, is going to be $75.70. So I'm going to go just a little bit higher than that for my Y max value, and maybe use 80. And so I'll go back to the graphing calculator, and we'll change Y max to 80. And I'll up the Y scale a little bit. Perhaps each tick mark will be worth 10 units. And let's go ahead and press graph. And there is the part of the line for the cost equation that is relevant to all the conditions that they've imposed on us. All right, so obviously the line incorporates the slope, the y-intercept. We can see that the y-intercept is a little bit higher than the origin. Okay, that's why I actually use y min as 0, so that we can see that the y-intercept is not 0, but rather something a little bit larger than it. And we also took into account that the X values have to range from 0 and 800. So this is a graph of the equation when we factor all that into the graphing calculator. And are you guys coming up with a similar looking graph? All right. So I'm going to go back to the notes and just sketch this out as best as I can. I'll indicate the rest of the window settings. X min was 0, X max was 800. And again, we got those values from this compound inequality as part of Part A's instructions. We went by 100, we went by 100s, I should say, on the x-axis, just so that there aren't like, 800 tick marks on it. And then y min was 0. That helped illustrate the y-intercept. And y max was 80. Okay, that's based on plugging in the x max value. And then we went by tens on the y-axis. I'll sketch all that out, and I'll indicate some of these window setting values as tick marks. So x max was 800, x min was 0, so was y min, and y max is 80. And I'd also like to indicate what each axis really represents. So the x-axis, I'll mark this as x, and in parentheses, I'm just going to indicate that the x values represent different kilowatt hour amounts. And kilowatt hour notation, if you don't want to write out the entire thing, is lowercase k, capital W, and then lowercase h. And that stands for kilowatt hours. Okay, so these are different electricity amounts going along the x-axis. The y-axis is going to get replaced or renamed as a c-axis, since the y values represent the different costs, and I'll indicate just that. And last but not least, our line, okay, which started a little bit higher than the origin and increased its way all the way up to the very far right of our calculator screen. And that would be a sketch of y1, which is our cost equation. Does that all make sense? That's watt I'm talking about. Get it? Watt. All right, so let's do one more application problem. And I'm going to get us started with it, but then have you guys work on the rest as best as you can. All right, completely different context here. So we're talking about a report in Child Trends database. This is real data, by the way, at least I'm fairly confident it is. Nice thing about what our author does is he references where he gets the data from, and just based on working with the textbook for many years now, a lot of it is real life data. Some of the stuff, or most of it, isn't made up. So I don't know where he gets this data from, but I'm sure that it's referenced in our textbook. But I guess that's neither here nor there. Here's what we're looking at. The report indicated that in 2000, 20.6% of 12th grade students reported daily use of cigarettes, whereas in 2013, 8.5% of 12th grade students reported daily use of cigarettes. And so just based on that, we can get a sense that the percentages are going down over the years. There could be a variety of reasons for that. My favorite one is, they're vaping nowadays instead of using cigarettes. We're just messing about that. But anyway, in part A, so write a linear equation that relates the percentage y. Okay, so our y values stand for the percentages. And we don't have to convert them to decimals if we don't want to. We can just leave them in their current format. The percentage y of 12th grade students who reported smoking cigarettes daily to the number x, which represents years after 2000. Okay. So start this out. let's construct a table, much like we did in the last problem. They don't want us to use replacement variables for x and y. But they do want a linear equation. And we can assume that they want it in the format y equals mx plus b. Now we're not going to change any of these variables. They still want us to use the variable y and also the variable x. So in the table, label the first column as x and the second column as y. We have to be careful about our values of x. The values of x represent number of years after 2000. We do have an indication of two x values that we can put in this table. Anybody want to take a stab at what those two x values are? Okay, 0 is one of them. Yep. I'm thinking something different. 13. So yeah, 0 and 13. So if they provided a rate of change for us, like they did in the last problem, when they said 0.057 dollars per kilowatt hour, I would, defer to using 0 and 1. But if we look at, the first couple of sentences for this problem, it says here that in 2000, 20.6% of 12th grade students. So that 2000 would correspond to an x value of 0. And as you might expect, the 20.6%, that's a particular y value. Specifically, it's the y value that corresponds to x equals 0. So we could use 20.6 for that. And then in the second sentence, 2013 would correspond to an x value of 13, and the corresponding y value would be 8.5%. Now what's helpful about this is that even though we don't have the graph of the linear equation, we can assume 2 points on it, 0, 20.6, and 13, 8.5. And that's about as far as I'm going to go with setting it up. Keep in mind our goal is to get the equation in the format y equals mx plus b, which means you want to find the slope m and also what the y-intercept is. And we have enough information here at this point for you guys to be able to calculate those two. Well, you'd calculate m, but b is actually hidden within our table. So I'm going to kick that off to you folks. And if you want to proceed to taking care of parts B and C after you're done, you're more than welcome to. But before you guys get started on it, when you go to calculate slope, you'll probably want to round it to 2 decimal places. Okay, so there's going to be some rounding that you'll want to do for the slope, and my recommendation would be 2 decimal places. Okay, so I'm going to give you some time to work on the rest of this, and in just a little bit, I'll jump back in and we'll see how we did, okay? All right, go ahead and knock it out. All right, I'm going to jot down my solution to part A. Let me know if you have any questions along the way. All right, what do you folks think about y equals negative 0.93x plus 20.6? Fraction form be fine, yep. It might help to maybe use it in decimal form for part B though. But if you leave it in fraction form for part C and then convert to a decimal after, you'll probably have a more accurate answer than what I have. But we'll be really close. But anybody else getting similar results here? Everybody good? All right, cool. So that's our equation. Keep in mind what y represents. It's a percentage of 12th grade students who reported smoking cigarettes daily. Okay, so let's see how we can tie that into part B where it says interpret the slope of the line. And I'm going to use the decimal version of it. So m is approximately negative 0.93. And as we were doing the last example, not part A, but the one from the last page, I'm going to set this on top of 1. And the negative 0.93 would represent a change in y, or change in percent of 12th graders reporting. And then the 1 would represent change in x. Does anybody want to offer what they think the interpretation of the slope might be with this information? So remember, we're going to want to interpret from bottom to top. And this 1 might help to indicate that it's positive, meaning that each year we go past the year 2000, okay, the percent of 12th graders reporting decreases by 0.93%. The reason why it would be decreasing is because the number in the numerator is negative. And so if you think about plotting the line using rise over run, and we'd have to go down by 0.93 and then to the right by 1, that's an indication of, for each year we increase, the percent goes down by roughly 0.93%. I'm going to put it this way. For each additional year, beyond 2000, the percent goes down by about 0.93%. Would that be a reasonable statement? Does it make sense to you? It doesn't have, for your interpretation, doesn't have to be word for word, something to the effect, just indicating the relationship between the numerator and denominator, all right, as it applies to our application setting. For part C, they want us to predict the percent for the year 2025. And then a couple of follow-up questions. Is the result reasonable? Why or why not? How would we start this one out? Close. I do like your thinking. So I think you're probably basing that on 2025. Yeah, there we go, 25, yep. So 2025 would correspond to an x value of 25. Okay, so we're not gonna, plug 2025, that specific year, into our equation because ours is based on the number of years past 2000. So we'd want to translate 2025 to just x equals 25. And when we do that, we can plug it in. Y equals negative 0.93x, which in this case is 25, plus 20.6. And when I crank this out, I get negative 2.65. Did I get confirmation on that? Rock on. Now, keep in mind what the y values stand for. This is, in our application setting, negative 2.65%. So that would be the prediction for the year 2025. Is it reasonable? Why or why not? So I'd like to hear from you guys. Yeah, that would be kind of a strange scenario, right? Negative 2.65 cigarettes. Now, we're based this prediction on our equation. So, the y values are dictated by the equation. So mathematically, the percent for the year 2025 is negative 2.65%. That's mathematically. Realistically, yeah, I would, consider a different value for 2025 than what our model is predicting. So basically, no, this is not reasonable. But keep in mind what the negative 2.65 represents, right? Negative 2.65 represents negative 2.65%. So percent of what? Okay, so what is the y value tracking? The y value is tracking the number of 12th grade students reporting, right? So I wouldn't say you can't smoke negative 2.65 cigarettes, even though I totally agree on that. I would say something to the effect that you can't have a negative amount of, a negative percent of students reporting. Okay, so the y values are based on, the percent of 12th graders reporting. Okay, so I would say, not reasonable, first of all. And as justification, I'll just put you can't have a negative percent of people providing reports. or something in the ballpark of that. Make sense? Kevin, did that clarify? Alrighty.